All right, so in this next question, we're going to see what happens if the cow, instead of just sliding down, if she gets a running start as she slides down. So let's go back and make our hill. There's our cow on the hill. There's our arbitrary h equals 0 level. That is the level from which we're going to measure height. And we'll do that. We know the hill is 10 meters high. And there sits our cow. She's going to get a running start, and so she's moving at point A this time. And we again want to know how fast will she be moving at point B. If the cow gets a running start, 6 meters per second, how fast should she be going at the bottom of the hill if she slides down it? Let's again do a couple of pie charts, because the pie charts can help us build our conservation of energy equation. So this is for point A, and this is for point B. All right, so initially she's moving, that is at the top of the hill at point A, but she's also up on the hill. Now, I don't know if 50-50 is the right split, but it gets the idea that some of her energy is stored kinetically and some positionally. Now, there's no friction yet. We'll put friction in eventually. And so at the bottom of the hill, she is no longer above the h equals 0 level. She's no longer at some height, and so all of her energy is stored kinetically. And conservation of energy tells us those two pies must be the same size. Okay, so we can write out our mechanically stored energy, our conservation of energy equation. In general, it looks like this. In general, it looks like this. Plus work equals the ending mechanically stored energy. This is going to be KE initial, or at point A, plus PE at point A equals the KE at point B. And you can just see that right from the pies, B and the stuff for A. Now this is going to be 1/2 mv squared velocity at A plus the PE at A, mgh equals 1/2 mv squared. That is at point B, and that's what we're interested in. Subbing in the numbers, 1/2 times 500 times 6 squared. We've calculated this before. Let's save a little time. That's 49,000 joules. And this will be 1/2 500 times dB squared. Now you go ahead and calculate what dB is.
Good morning, this is a reminder.
And I got 15.2 meters per second. 15.2 meters per second for a velocity at point B. So clearly it makes sense. If the cow gets a running start, they're going to be going faster at the bottom. It's no different than if you start at the top on a sled and slide down versus getting a running start and doing a belly flop and head on down. You'll be going much faster at the bottom. Let's take a look at yet another example. All right, in this case, our cow is now finally going to encounter a slightly more realistic situation, which is that she's going to encounter 1,500 newtons of friction force. That's 10. And for the sake of this part of the problem, let's assume that the length of the hill there is 20 meters. That would imply that's about a 30-degree angle. Again, that's a part that is we could consider a given in the problem. All right, so in this case, the pie charts would look something like this. Again, there's our h equals 0 level. Here's our point A and our point B at the bottom, because again, we want to know how fast she's going at the bottom. So it makes sense to do it like that. So at point A, the energy is stored positionally and kinetically. And at point B, it's stored kinetically and thermally, because as she ran over the ground and there was some friction, caused things to warm up. So she's not going as fast as she otherwise would be. Let's set up a conservation of energy equation that reflects that. PE at point A plus KE at point A. And now there's energy transferred from mechanical storage, so there's going to be work done. And that will equal KE at point B. In the next segment, we'll take a continued look at this.